Swayam Prabha. Digital India. Educated India.
Welcome to the second lecture of week 3. In this class, in this lecture, we are going to talk about, for the first time, about the constituent elements of a muffler. What are the basic elements that constitute a muffler? But before we do that, we need to again revisit some expressions for the acoustic pressure, planar waves for propagation in one-dimensional ducts, as well as the expression for acoustic particle velocity along the same direction, and develop a relation between acoustic pressure and acoustic particle velocity and the progressive wave variables, and talk about impedance, relate the impedance at different sections of a tube and derive some meanings, and then talk about different elements like a lumped mass approximations and different parameters that constitute different measures, basically metrics that using which we evaluate the performance of mufflers. So, let us begin with the one dimensional duct case, one dimensional duct. So, let us say we have wave propagation in a one dimensional duct, and you have certain waves which go like this. So, the acoustic pressure then is your P x, which is nothing but A into e to the power minus j k naught x plus B into e to the power j k naught x. So, like I have been mentioning, A and B are your amplitude of waves that propagate in the positive x direction, this propagates in the negative x direction. Okay. All right. So, we have seen that using Euler equations, you have certain things. So, this will basically lead us, and once we assume time harmonicity and all that, eventually you will end up with A e to the power minus j k naught x minus e to the power j k naught x. So, let me write down this thing very clearly. This is something like this. So, we need to make some meaning out of it. This is what it is. Okay. Now, this thing can be written in the form of mass velocity, if you recall the last week's lecture. So, V x is nothing but 1 by y naught into A e to the power minus j k naught x plus B j k naught x, where y naught is C naught divided by cross section area S, and k naught is your wave number. Okay. So, we will actually use this relation, this one and this one, to derive certain relationships. Let me call this 1, let me call this as 2. Basically, the impedance at any point, let us call this distance as x, and this is 0, this is L perhaps. So, the impedance then at any point z x can be written as P by V, which is nothing but A minus j k naught x plus V j k naught x and A power minus j k naught x, and here you have minus j k naught x, and what happens in the numerator is y naught, because y naught goes up. So, z at 0 is nothing but y naught times a plus b divided by a minus b. So, this is multiplied. So, keep this aside, we will derive some meaningful things, and it is easy to see that at x is equal to L, this end might be open or it might be closed. It might be closed with a rigid termination. We will see what happens by giving it different values of z. So, z at a distance L is given by into e to the power minus j k naught L plus b into e to the power j k naught L, and a into e to the power j k naught L minus b into j k naught L. So, we use complex exponential. E j theta is your nothing but c plus j s, that is nothing but cos theta plus j sin theta, Euler formula. So, once we do that and do the maths, do the algebra, what are we going to get? We can simplify this further to get a plus b times cos k naught L minus j times a minus b times sin k naught L, and a minus b times cos k naught L minus j times a minus b times sin k naught L. So, once we simplify this thing further, what are we going to get? We will probably end up with a plus b times a minus b. So, this thing we will keep and 1 minus a plus b times a minus b times j tan k naught L. So, this is the general expression for impedance at a section L, which relates the progressive wave variables A and B amplitudes and the wave number k naught with the length L and the impedance at this thing at this point. So, we can actually non-dimensionalize it and write this as Z L divided by y naught is equal to Z naught at Z is equal to 0 divided by y naught minus j tan k naught L times 1 minus j times Z naught divided by y k naught tan k naught L. We can do this. So, basically if we were to simplify this thing further, we will get, that is, if we were to express Z naught in terms of Z L with some simplifications, we would get Z L by y naught plus j times tan k naught L 1 plus j times Z L by y naught into tan k naught L. So, where are we heading towards? Or probably Z naught is your Z L times cos k naught L plus j sin k naught L times j Z L by y naught into sin of k naught L plus cos of k naught L. So, this expression is of significance to us, and we will probably call this as number 3, because now if we again recall our system that we have got, this is the duct at x is equal to 0 and x is equal to L. Suppose if we fix up this end, so if we consider a duct like this, if we have a duct like this, and if we if we have a duct like this and if we block the end here, so and do a piston excitation here or a loudspeaker. So, what does the rigid surface do? What does the rigid surface do? It basically means that the velocity normal to the surface is 0, that is u n or u here is 0. So, when u is 0, what does it mean acoustically? It means P by u is z. So, if u is tending to 0, that means z is tending to infinity. What we see here, if we have a piston doing to and fro motion, and if we have a rigid surface on the other side, we will see the infinite impedance at this surface in terms of the impedance perceived at x is equal to 0 or z is equal to 0 n, that we can nicely evaluate by taking this particular term tends to infinity, so does this one, and so these terms, the underlying terms, they are negligible in comparison to these ones. So, what will we get eventually? You will get Z0 is equal to minus j y naught into cot k naught L. So, here we are taking j in the numerator and y naught goes also in the numerator, cos by sine. So, this is what we are getting. So, for a closed cavity of length L, and we are doing piston excitation here back and forth. So, at this stage, at this point, we are going to get this Z naught is pretty much given by this expression. So, we can draw a lot of conclusions out of it. So, at this point, the expression is this thing. So, if Z naught is tending to 0, that means at those frequencies we can solve for k naught for which Z naught is 0. So, when we do that, cot k naught L is 0 means what? Cos k naught L by sin k naught L, that is 0. So, this will happen when this is going to 0. So, that is cos k naught L is going to 0, and this will happen when we have 2 n plus 1 pi by 2, where n starts from 0, 1, 2, 3, 4 like this. So, k naught L is 2 n plus 1 by pi by 2. So, your k naught or f becomes 2 pi f by c naught times L is 2 n plus 1 pi by 2. This goes away, and once we simplify this thing further, such a frequency, I would call this resonance frequency, is given by 2 n plus 1 by C naught by 4 L. So, clearly the first resonance frequency can be obtained by setting n is equal to 0. So, you get C naught by 4 L as the first resonance frequency. Then if you put n is equal to 1, you are going to get 3 by 4 L into C naught and so on. So, this is what we are going to get. So, what it means is that we have a certain side branch like this, and if we have a tube system which say, let us say, goes to infinity, and there is a certain wave coming from this direction, and we have a blocked end here. For certain frequencies given by Fr, and this is the length is L. So, if we have length L and waves are coming here, and so for certain frequencies given by C naught by 4 L, 3 by 4 into C naught by L and so on, all the waves will be diverted here and nothing will propagate downstream. That is the path of least resistance, what most of us do. So, basically all the acoustic power goes in along the side branches, and very less power is transmitted downstream this thing. So, these are also called quarter wave resonators, because for certain frequencies which is given by C naught by 4 L and its multiples and its odd multiples, all the acoustic power goes in the direction of the duct, and very less power is transmitted. So, using this principle you can control, you can achieve certain tonal noise control. So, in a way we can also think of this particular expression like L is equal to C naught by 4 F R, where L is given by then lambda r by 4. Lambda r, why? Because wavelength is C naught by F r. So, we are just trying to put this particular thing in here, and so length should be quarter of a wavelength. So, wavelength can obviously vary, it will vary with frequency. So, for specific wavelength or for specific tones, certain tonal frequencies, complete noise control can be obtained theoretically. However, life is generally not simple, and you have typically no material is rigid, what I mean to say. So, whatever you are assuming this as rigid, it is usually not rigid. The end plates usually, no matter how thick they are, after all they have some finite impedance, that is acoustic velocity, or the structural velocity will never be 0, you will always have certain structural, certain velocity of vibration of this. So, as a result we will probably experience an impedance which is not infinity here at this point or finite, and then we have to consider the effect of end plate vibration. So, that will basically complicate problems, and this is important because not only in the side branch resonators the noise is radiated by in these direction, in all directions, we also have typically things like the end plates of mufflers. So, no matter how thick or properly you weld them, it is going to vibrate a bit, and that is going to have a major effect on the structural acoustics part, or the breakout noise, what it is called. We will talk about that probably sometime later, but another expression we can probably derive quickly for the impedance. So, if you were to define the reflection coefficient R, which is obviously a complex quantity, and let us denote this in terms of this. This is your reflection coefficient, okay. And if we denote this at 0 by B by A, because the reason I am saying this 0, because it is e to the power j k naught x, e to the power minus j k naught x. If you put x is equal to 0, you are going to get B by A, and at R L we are going to get e to the power 2 j k naught L. So, with this thing, if we simplify, if we put in our old expression for Z is generally like this, we are going to get something like 1 plus R minus 1 minus R, something like this. And if we simplify this thing further, reflection coefficient then is Z, or general Z minus y naught divided by Z plus y naught, and so this will be valid for any x. All right. So, obviously, when we have things like R rigid termination, we have this tending to 1. We have this tends to 1, because then your Z thing that is tending to infinity. So, this only this term will contribute, will be dominant, and what it means that the entire wave is reflected back without suffering any phase change or something like that. So, therefore, a perfectly rigid termination reflects the incident waves with the same amplitude and phase. Another termination that is very important in muffler acoustics is the anechoic termination. So, what we saw in this slide, let me draw it again for you. Rigid termination is of course like this, it is blocked end completely. Another termination, so whatever waves are going here, whatever waves are striking here, same thing is coming back B. Okay. Now, another termination that is used very often in muffler acoustics is basically your anechoic termination. So, it is typically drawn like this. you have wave like this. So, what it means, nothing comes back. So, this motion is not allowed, only A is allowed, B is 0. That is, no matter how loud the sound is or whatever the condition is, whatever goes inside this termination is completely absorbed by these linings. Basically, they are nothing but mineral wool, glass wool or some absorbent material. So, whatever, all this while this is a rigid termination, rigid cylindrical duct made of steel or brass or whatever it is, and here you have a conical kind of a termination, conical annular area filled with rock wool, glass wool or some dissipative stuff, and as the wave traverses through this path, and obviously I forgot to mention one thing here, they are not obviously solid tubes, they are perforated. So, you see perforated tube. So, typically by perforate we means these small holes will be there along the curved surface area. The waves going inside can interact with the stuff that is outside through these holes. That is what is going to happen here. The waves, they enter these holes and they get dissipated. Most of the acoustic power is dissipated, but again the termination being anechoic, or the principle or the ability of the termination to completely prevent or suppress the waves that travel in the backward direction, it depends on its construction, the material, the flare angle theta or whatever, the number of parameters, and obviously frequencies. So, the point I am trying to make is that no termination is perfectly anechoic for all frequencies, it depends on the frequency. So, we need to design it properly based on a lot of experiments. So, the idea is that we can consider a termination anechoic beyond a certain frequency, much in the same manner what acoustic chambers or anechoic chambers are designed. So, this termination is used in setting up a muffler testing rig, anechoic termination using some parameters which we will cover later. So, equivalent of a tube with anechoic termination equals characteristic impedance of a tube. So, when we basically, let us go back to this expression. So, when we put reflection coefficient to 0, that is R is 0, because if we define R is basically nothing but e to the power whatever it was and a to the power whatever it was. So, if you put the numerator 0, we are going to get R is equal to 0. Once you put this R is 0 here, what are we going to get? We are going to get Z is equal to Y naught, that is the impedance at any point is equal to the characteristic impedance of the tube. Much like the free field, we have rho naught C naught, here you have Y naught by S cross section area. So, it depends on the sound speed as well as the cross sectional area of the duct. So, because this is not surprising, because we have only here a progressive or the forward travelling wave. So, another thing before we move on with the other elements is the radiation impedance. I am just going to talk about that very briefly. Radiation impedance is nothing but the impedance imposed by the atmosphere on the acoustic radiation of the end tube. So, obviously a full fledged 3-dimension analysis is required. So, if we have a certain tube, a lot of work has been done. So, on this, so if you have a tube and some wave is coming out here, and this is your termination. So, what happens here is that this is a baffled termination, and another termination that happens is your wave is coming out and is suddenly exposed to the big atmosphere. So, the radiation impedance is nothing but at this point, let me draw it with a black mark here. So, it is nothing but your Z is equal to P by U at say 0 for both cases. This one is case A and case B. So, this impedance, radiation impedance for the baffled case as well as for the unbaffled case is a classical point of study, and a lot of work has been done in this regard. So, what I will probably do is that just present certain expressions for the radiation impedance without bothering to derive them. That is beyond the scope of the present course, although classical texts are available in this one. I will define the meanings of the symbols. So, Z naught is equal to the radiation impedance, that is the impedance that is seen by the wave which is just incident here, that is P by U what is the impedance or the opposition by the atmosphere to the propagation of the wave. It is a complex number as usual, because the reason is that no termination is anechoic, no termination is fully rigid. You know, if you consider a simple case, if you have a pipe and exposed to the atmosphere, just at the exit of the pipe, the atmosphere or the surrounding air will pose an impedance. So, some waves will be reflected back, some waves will be transmitted downstream. So, it is a kind of a midway between a rigid termination as well as a anechoic termination. There are other terminations also, of course, called open end termination, where P is 0, where P is 0 then Z is 0. So, that is also an extreme case, but the more realistic thing is to develop suitable models, because here also there is air, here also there is air, the density might be different based on the temperature of the exhaust gas. But the point is that we have a pretty complex expression for R naught and X naught in terms of some Bessel functions given in the classical text. So, for the case of termination which has an infinite flange, basically a baffled termination like this one, I would say this as baffled. So, here you have only baffled plate. So, here you have only the hemispherical space available, not the full spherical space. So, for such a case R naught is given by Y naught times 1 minus 2 times J 1 times 2 K naught R naught divided by 2 K naught R naught. So, where J 1 is your Bessel function, of order 1 and first kind. So, when you do this, you will probably get 2 K naught R naught square divided by 2 into 4. So, minus 2 K naught R naught to the power 4. Basically, you are doing nothing but writing down the first few terms of the Bessel series in terms of the Frobenius series solution. So, like this you will have many more terms. So, similarly, X naught can be given as 4 by pi times 2 K naught R naught times 3 minus 2 K naught R naught cube by 3 square into 5 plus 2 K naught R naught to the power 5 by 3 square into 5 square into 7 and so on. So, where Y naught of course is your characteristic impedance of the duct, and this is pi by R naught square, and R naught is the radius of the duct, that is your this thing here R naught. So, once we simplify it, that is for low frequency, some simplification is possible, because you see typically in automobile mufflers the radius is not very large, it is typically about, the diameter is about 50 mm at the max, 50-55 mm. So, radius can be 25 to 30 mm, something between that. So, and the fact that the engine noise is concentrated mostly at the firing frequencies of the first few harmonics of that, K naught R naught is typically small. So, it is less than 0.5 or so. Under such a condition, the real part of the radiation impedance becomes this thing, and X naught is 0.85 times K naught R naught. This is what we are going to get. So, Z naught then becomes R naught plus J X naught, and this is Y naught, this 1 minus R. So, we can derive all sorts of this thing, and this particular expression is useful when if we were to evaluate the thing called insertion loss. So, if we know the radiation impedance, it will be good. Similarly, another expression for the unbaffled case, that is basically or this case, which is much more complex and derived in a paper published a long time back. This is sort of given by your for of course low frequencies, K naught R naught is less than 0.5 for the unbaffled case. is given by Z naught is Y naught divided by Y naught into K naught R square by 4 plus J times 0.6 K naught R naught, where K naught R naught is less than 0.5. So, you will have those sort of arguments. Now, we will stop in this lecture here and probably resume in the next lecture, where we will talk about different elements that constitute the muffler, sudden area expansions, and but actually before we do that, we will probably have a look at the different measures to evaluate the muffler performance, like insertion loss, transmission loss, level difference, and so on. It is probably then will be a good idea to talk about the different constituting elements of a muffler. So, I will probably stop here, and I will see you in the next class.